NIyantra team number 69. Introducing ourselves, I am Zen Kapadia.
I am Mansi Jain.
I am Sameer Garote.
And I am Suresh Manian.
And our project is a task learning robot which involves making a socially intelligent robot and which can be used to assist humans and increase the efficiency of work and can also be used for industrial automation.
We have made a generic algorithm to train any robotic arm. We have used user-friendly GUI at LabVIEW, which does not require any graphicals, any skill and programming.
Have been envisioned to assist humans, and for that it may require to learn new tasks and skills from people who do not have or have little experience in the underlying technology. The challenge is to build socially intelligent robots who can help humans achieve their tasks, and we have taken this step forward to accomplish this challenge. I'll be explaining the task learning process. These encoder and vision values that are received from the robotic arm act as feedback and are streamed to the MyRIO, which is the processor. Now, in order to learn a particular task, the robot must have memory, and we prefer storing these data in the form of files over the PC. So we have to create a network stream which enables the flow of data from MyRIO to PC. So now during the running phase, this data from the file is called back by the MyRIO, which are further passed to robotic arm algorithms which generate suitable controls for the robotic arm in order to control it autonomously. We also have made a user interface on the PC itself, which is very, very user friendly.
That electronics implemented in this robotic arm. This robotic arm has total 6 motors, and each motor works on 24 volt and 5 ampere continuous current of 5 ampere. So we have to use this motor drivers, which acts like interface between this MyRIO and this robotic arm. So here you can see this is a shield which acts like interface between this MyRIO board and this robotic arm. It has level converters and buffers. Since the output of MyRIO is 3.3 volt compatible and the input of VNH motor drivers are 5 volt compatible, so we have used these buffers and level converters. And here you can see these are the connectors through which supply goes to this robotic arm, and this black colored box is nothing but a 24 volt power supply. So advantage of using MyRIO over all the other boards is it has multiple number of IO pins. It has 4 encoder channels which works really very efficiently, and it has a one USB port which makes the interfacing of the device really very easy.
We are controlling the industrial robotic arms Corvo TR7 with the MyRIO board, and we have interfaced all the motors on this MyRIO board, and we are actually controlling it using a joystick, and this joystick connects via USB to the MyRIO board. The MyRIO toolkit has a USB host VIS, which makes it much easier to interface any of the USB devices like this joystick or a webcam. We have used all the 4 channels of the encoders on the MyRIO board to get the readings of the encoders of this robot of the robotic arm, and by getting these readings we can actually map it to specific angles. So I can know the angle of any of the part of the arm with respect to ground. The problem we faced with this robotic arm was that during the downward motion of this elbow, because of its weight, the speed was increasing, and this disturbed my encoder readings. So we had to incorporate PID control to maintain a constant speed of this arm. So for PID control, we have set the set point to a specific speed which we need to maintain it, and my process variable is the omega or the angular velocity of the robotic arm. And by setting the appropriate PID gain parameters, I am actually generating a PWM signal, which is then again fed back to my motors. So that's how we overcome the problem of the weight.
So now we are incorporating vision into the scoreboard. We have used the technique of color segmentation by thresholding. This VI gives us the space coordinates of the ball that is tracked. Also gives us the bounding box of the ball. Also gives us the area of the object as well as the center, as well as displacement of the ball from the center of the screen. We have also used PID algorithm so that the scoreboard can track the ball efficiently. I'll be demonstrating it. This is the VI for forward kinematics, which gives you the coordinates of the gripper as per the orientation of the arm. So I will run this VI now. If you input any angle for say the base or for the shoulder and for the elbow and for the wrist. So this will give you the actual coordinates of the gripper in centimeters as per the XYZ axis. This is the VI for axis transformation, which links your vision values and ultrasonic values and passes them on to inverse kinematics, which will be explained soon. So here I demonstrate the VI. If you have your camera X displacement, the centroid of the object is detected as suppose say 4 centimeters from the center of the frame, 5 centimeters, and your Y displacement as 4 centimeters, and suppose your ultrasonic sensor senses it at a distance of 17 centimeters. So, and having these angles as the transformation angles, you get the final result. This VI actually demonstrates the way that these are the magnitudes of the inputs that we get from vision and ultrasonic sensors, and this VI basically gives these magnitudes some direction in which we have to add it in order to apply inverse kinematics. For inverse kinematics gives you the orientation of the arm in order to reach a particular object given its space coordinates. Now using vision and ultrasonic sensors and by passing it through axis transformations that I had introduced earlier, we will get the exact space coordinates of the object, and in order to reach that particular space coordinate, we want to determine what should be the orientation of the arm. So here I will demonstrate the VI. Suppose say these are the inputs from forward kinematics that we get, and these are the inputs that we get from vision and ultrasonic sensors after axis transformations. These will be the current encoder values, and by using this we get the final coordinate of the grip of the object, and we get the orientation of the arm to reach this particular coordinate. So all these three VIs that I have demonstrated right now will be soon implemented over the scoreboard, and you will be able to see the final result. All the modules and algorithms that were described earlier are now clubbed into one big VI, where we are trying to track this ball autonomously and the bot will grab it. So I'm setting the HSP values of the ball. The bot can see the ball now, and on switching on the motors, using inverse kinematics, the bot will come forward and try to grab the ball. As you can see, it is a little erroneous for now, and we will try to improve upon it soon.
In our project to store values of encoder and vision because while training, and we have to retrieve those values while performing. So to connect between MyRIO and PC, we are using network streams. We are keeping the file on PC because the GUI is on PC, so it is easy to verify and retrieve the data. This is how the VI works. These are the data which I am inputting. Here it is getting stored. Now we will read back this data from this file to this file. When I press this boolean, the data will be stored in a file in LabVIEW data called F1. This is where the data is stored. Now when I press this boolean, the data will be transferred from this file to this file.
We have made this user interface for controlling the scoreboard as well as training it. We have tried to make it as user friendly as possible. Now coming to the VI, I will describe you. We have given tab control options for control as well as training the scoreboard, and within train we have incorporated training the scoreboard within steps so that it reduces the complexity and makes it easy for the trainer. We have also given options for normal training where he can train by storing encoder values, and we can also train the scoreboard using vision. So now let's start training. So now let's go to step 1 and save the move the bot please. Now let's save this data. Let's go to next step 2. We save this data as well. Now let's go to step 3. We save this data. Let's go to step 4. We save this data. Let's go to step 5. We save this data as well. The initial and final values of the encoders are getting saved here. Let's go to step 6. We save this data as well. So this is our task that we want to do, going from location A to location B. Now I want to perform it 2 times. So now let's run the bot. So this is the complete process of task learning.
The future scope of our project.
Several robotic arms like these can be set up on an assembly line, and they can be made to work synchronously. And since the MyRIO board has been equipped with a Wi-Fi module, these robotic arms can communicate with each other using Internet of Things to perform a task synchronously.
We can also incorporate safety into this arm. If there is any external stimulus or human presence detected, this arm can either slow down its motion or stop.
We can also incorporate artificial intelligence for better results. We are using machine learning for getting better results of vision and neural networks to communicate easily between the 2 robots.
Thank you.